In this part, we are going just to give you for reference the basic expressions that will support those fields you have seen before in the animations. So with this, you may have some idea of the calculus that is involved in them. First of all, as you saw in the last one, let's consider the case of a charge that is moving along the path with in the case of uniform motion. That means that the velocity is constant. All right? So here, once again, we have the charge, and here we have the point where we want to see the fields. And the charge moves along this path without acceleration. So to represent the motion, we just need to know a point where the charge is at a certain time and the velocity. In this case, let's denote this axis as c. So we say that the velocity is just a vector along the c-axis. The observer here will sense a field produced by this charge that will have to travel this path, this distance r. So this is just r. And it will travel along this path at the speed of light. Problem is that while the charge is producing this field and the field reaches this point, the charge moves to a different point. And now you see that to know where the charge is, the only thing you have to do is to multiply the velocity times the time that is involved in this travel. That's the travel time, that we have also called this time the delay or the time delay involved. And this is nothing more than the velocity times the distance, this distance, divided by the speed of light. And the charge now is at this point. To write the expressions for the fields in a simple way, we have just to project this point. And we just project in this direction. And this is just, if you see this point, this vector here is just the dot product, the scalar product of this r times the velocity divided by c, which is basically the projection of this point. And we call S at this segment here. Now, we have also the possibility, since this trajectory is very well known, we could also write the distance to the charge not at the previous time, but at the retarded, at the present, at the moment. So for us, we may say also that the field we receive, although it was produced at this point, will be such as if it were produced at this point. And we use this as, this term S, to represent it. With this, and this is just definition for those projections, we write the field, and this is just the expression for the field. Here we have a dependence on r, and this is the cubic power of the distance. And then you see here the velocity of the charge. And this is going to be interesting because if this velocity approaches the speed of light, what happens? That this term will become smaller and smaller. If this is very small compared to c, then we basically have this term. This is the electric field. Now we can also write this field in a less compact way, getting rid of this term here and taking just this distance and the angle theta that is here between those, the trajectory and the charge observer. And with this, you see that the field just falls off as the square, inversely proportional to the square of the distance. And it depends on the angles and the ratio of the velocities. There's also a magnetic field that has this expression, and since it's proportional, this is the cross product we commented before. So this field will also fall off with the same law. And this is just the basic numbers to write those fields. And the previous animation, those are the radial lines you saw before. Let me comment briefly on the two cases, very low velocity. And this is normally what happens when we have electrons moving along circuits. The electrons in the wires we have around, they move really slowly. In this case, things simplify and we go to very basic laws known from the static case. The name for those laws, for those of you that are familiar with electromagnetics, for the electric case is Coulomb's law. For the magnetic case is the Biot-Savart law. And once again, this is the same plot. The charge is here, is moving along this path. Uniform motion, once again. This is the vector to the observer. Here is the observer. The receiver, that is just in some way trying to know and extract information from this field. And here we have represented two vectors. One is the vector, the electric vector, electric field E, in red, that is pointing in this direction. And this is the magnetic field. And here we have a new notation to be introduced. If you look at this point, we have drawn a circle, and inside we have put a cross. If you are not familiar with vector representation, this is a very classical way to represent a vector that is not in the plane of the screen, is not on the plane of this figure. It's perpendicular. So the electric field, if this is your screen and the electric field is in here, this field is perpendicular, goes in this direction. And since we are representing vectors, if you want as arrows, they have a tip and they have a tail. And in the tail we have a cross. So looking at this plot, we may say that the electric field is going towards the screen. If it was coming out of the screen, then we'll be seeing the tip of the arrow of the vector, and we'll put there a point, a big dot with it. So this is just a notation. Here is the electric field, and we have the magnetic field that is perpendicular. And those, in summary, are the expressions for the electric field and for the magnetic field. That's what we have here. The other case, which is a different one, and we don't encounter this case in our circuits, in the devices and the gadgets we have around, but this happens in the universe frequently when we have electrons, for instance, expelled from the sun, and they will be traveling to the Earth in all directions of space at very high velocity. Normally they are close to the velocity of light. In this case, we normally say that those electrons are relativistic in the sense that their velocity approaches a value that requires relativity to be taken into account in studying them. And this is just going to be the case. And the expressions are valid for this case, the expressions we had before. I'm going to show you two examples. One is the case where the observer is in the path of the charge. This is to say the charge is going in this direction and the observer is looking how the charge approaches him. What happens here is the following. The charge moves in this direction. In the previous expression, the value for this angle is 0, and the electric field, that is radial field, points towards the observer. And this is just the value of the field. Depending on the velocity, if this is close to the velocity of light, this thing is closer to 0. So we have very weak fields in the direction of travel of the charge. I'm talking about general charge, but in most of the case you may say this is an electron, which is probably the most usual case. And there is no magnetic field in this case. The second example is where the observer is just perpendicular to the trajectory. It's like the charge going high in the sky, and we look up to the sky and see what happens. This is the plot, this is the trajectory. We are here. This is represented by our eye, but that's to say we are just watching these fields and trying to know this phenomena. And Here we have the electric field pointing toward the observer and the magnetic field that is perpendicular. And in this case, once again, going into the screen. The value for those fields is here. They once again fall off as 1 over r squared, but in this case, the values for those fields could be quite high depending on the velocity. So this is just the value. There's also a magnetic field, B, but although they are electric and magnetic fields, they are such that they do not transfer power. There is no power transfer in this process. So as the charge moves along with uniform velocity, it could produce fields, certainly it does, but those fields do not carry power. That's an important factor. So don't go in the other way, saying if there's no power somewhere, they are not fields in there, because you may have fields, but not power transported by them.